So let's go on to talk about the ideal gas. So let's say we talk about the ideal gas law, PDA and NLT. Sorry, I need to introduce another formula also. But first of all, let's go back to the definition of ideal gas. So ideal gas, you think that this definition is so dumb. So ideal gas is a gas which obeys ideal gas law.
So by default, we refer to gas as ideal gas.
Yeah. So for ideal gas law, yesterday we learned about this one. I don't want to repeat the definition or what are those quantities in the formula.
So what do they all?
So it has enough form. So it's a big N KT. The big N is the number of molecules. K is another constant. We call the Boltzmann's constant. You don't need to know how to spell it. You can just find it in a calculator. And actually, you can see that there's some conversion between the K and R. There must be some conversion. Now, you compare the common terms. No. You're comparing the terms in these two formula. You can definitely see that NR equal to big NK, is it?
Yeah.
The big N divided by small n will be the Avogadro's constant. So that's how we convert this formula. Yeah. Okay. No, you can just get it from calculator for R and K, and also the formula sheet. But something else for ideal gas.
So how many laws did we learn yesterday? I was like,
Not much. I don't think we learned a lot.
Right?
I don't think we learned a lot yesterday.
Yeah, sure we did.
Yeah, almost like just this formula for this topic, and also about the thermodynamics first law. The change in inherent energy equals sum of heat and work done. Do you remember? No? Work done. Now for ideal gas, so there's some other properties about the ideal gas. The first one, we will say that the size of the molecule is negligible. Temperature in Kelvin. No. You can't say it has no volume. You say you just negate those volume.
So these are assumptions, right?
Yeah.
Wait, when did we learn NR?
Like you say, comparing my weight to yours. My weight is negligible. No. So just compare my money to Li Ha-Xing's money, and then my money is negligible. It doesn't mean that I have no money, but although that is true.
So little, it doesn't matter.
Okay. You can't say there's no money. Okay. You can't say it has no money. I just has negligible money comparing to Elon Musk.
Have you seen the Chinese version? Elon Musk.
How? So what does mean by the size of the molecule? Oh.
I swear that's like a point.
I think Elon Musk always, he has a lot of children.
So could you repeat what that N, the small n and the big R?
Small n is the number of mole.
Number of mole?
Yeah. Number of mole.
So big N is the number of molecule?
Yeah. So these are the size of molecules.
Assumption.
What does R mean? I'm sorry.
Just a gas constant, just a constant.
Gas.
It's just a constant. But remember, so this is the size of molecule. And then this is the, this is the volume of molecule.
Empty space.
No, it should be, okay. So this is the volume of molecule. Sorry, the volume of the gas. No, I will say the volume of gas. So it means that means the volume of the container. No matter how much gas there is, we still treat the volume of gas equals the volume of container. Okay.
Last question, what does P mean?
Pressure times volume. Pressure times volume.
Sorry.
Now, the second thing is, the second properties about ideal gas is we ignore the intermolecular force. Oh, you have learned some intermolecular force in chemistry, do you? Not no, you just ignore it. Do you know the difference between ignore and no? You cannot say no, you just ignore it. Hmm? You just neglect those intermolecular force. And intermolecular force actually relates to one kind of energy, that is the potential energy. It just, you think about it when the water boils, it changes the state from liquid to gas. You need to break the bonding between the molecules. And that means you're increasing the potential energy of the water molecules. In that case, so breaking the bonding, and the bonding you know is related to the force. And then if we ignore the intermolecular force, that means there's no potential energy. For ideal gas, the potential energy will be 0. And this implies that if you still remember the internal energy, is sum of kinetic energy and potential energy. If we ignore the potential energy, that means the internal energy will be just the KE. We will need to use this result later on. But huh? Yeah. Why I can't smell it?
You see happiness and seeing stress.
Because I see you. Yeah. Go back to your seat. Let's move on. So, and we are going to the core parts of this chapter. So that is a kinetic theory of ideal gas. For ideal gas. So what is kinetic theory of ideal gas? Like you think about it like this. So you can measure pressure by using a pressure gauge. or you should call it the Boltzmann gauge. But indeed, you know what is the cause of the pressure? The gas pressure. Why there's a gas pressure? Because the air molecule is hitting the wall all the time. So it exerts a force on the wall. So if we sum up the forces by the molecules, and actually we can relate the speed of the molecule and the force. So that means actually what you want to do is want to use some microscopic quantity. And then when you sum it up, do you know this symbol? Yeah. So when you sum it up, then you can get the macroscopic quantity. So let's say for pressure, it's macroscopic. You're not talking about each molecule, the force of each molecule. But if you want to do, if you calculate the force by each molecule hitting the wall, and you sum it up, then actually you can get the pressure on the wall. Do you understand the concept behind? So you find the force by each molecule, and then you sum it up, then you get the pressure. Macroscopic or microscopic?
Macroscopic focuses on the overall.
Overall. So So for gas pressure, is a force due to the entire gas molecules hitting the wall. So we just sum up the force by each molecule, and then we can get some macroscopic quantity like the pressure. And also we want to relate it to the temperature, but later on we can see later on. So we do have some assumption for the kinetic theory of ideal gas. So first one, all the gas molecules are moving in a random motion. It's reasonable, is it? It's very weird that all the gas molecules moving in the same direction in this room. No, it's very weird. So second thing, So the next one is all the collisions are elastic.
Oh.
Yeah.
Why is it an assumption?
Why these are assumptions?
Why random motion is assumption?
This is a good question.
No.
No, because if they were ions, then they.
Now, I write down. You can see I write down a number them 1, 2, 3, 4, and later on when I prove this equation, you see that where I use this assumption. Just later on. Now, and then we say that all collisions are elastic. I'm not sure if you still remember what is mean by elastic collision. There's no kinetic energy lost. Yeah. I think this is also reasonable because the thing about the gas molecules are hitting the wall all the time. If they lost kinetic energy after each collision,
Air would just not move.
the air molecules just don't move. They lost all its KE. And then all the gas molecules sink on the ground. Yeah. So this is reasonable. So the third one, there is a time during collision. Is much less than the time between collision. I need to explain it, okay? So what does it mean by during collision?
When they hit.
Yeah, when it's touching, when the gas molecule is kissing touching the wall, then it's called the time during collision. But you're talking about time between collision. That means you're measuring the time, the first kiss and the second kiss. Okay. So let's draw a diagram. Let's draw a diagram.
Which by using double lesson, does that mean like a lot?
So we're talking about the time, for time between collision. Like you're talking about the collision with the same wall. We're talking about the collision with the same wall. So this is time between collision. Yeah, you're talking about time during collision. It's the time when it touching the wall. But in actually, you can ignore the time during collision all the time because
So small.
it's so small. And there's also some other assumption. I can't copy from there. These two assumptions are the assumption of ideal gas. So ignore the intermolecular force. To be more precise, except the time when they collide. The last one is ignore the size of molecule. So this is the kinetic field of ideal gas. So it also includes those assumptions in ideal gas. So 4 and 5 are the assumption of ideal gas. 1, 2, 3 are the assumption of kinetic theory. Okay. Oh, then let's move on. Oh, dun, 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 dun. Move on now, right? 好啦，嗱 ，indeed 咧，the gas molecule is moving in 3 dimensions. So it's not only in 1 dimension. So we can, let's say, draw a 3D diagram. I should have printed notes for you, but it's totally fine. Okay, it's better for you just copy once by yourself. Yeah. So we just consider as a container with a cube with the side L. And we're talking about the gas molecule hitting this wall, And then we do have we let the axis to be this is a C axis. This X. Whatever. This is a Y axis. Okay, this is a Y axis. Can you imagine it's a 3D? Yeah. It's a 3D. 冇問題。Why? No, this is a 3 dimension. This is a 3 dimension. So XYZ will be something like that. XYZ will be something like that. And so let's say if you're talking about hitting this wall, sorry. Then we'll just look at the velocity along the y-axis. We just look at the velocity along the y-axis. So C is We use a symbol C, that is the velocity of the gas molecule, right? And then, this velocity can be decomposed into 3 components. So Vz, Vy, and Vx. I can't, very difficult for me to draw it. Something like this. Just imagine. The C is a diagonal of this cuboid. Now remember, what does it mean by random? Random, it can mean that Vx, Vc, and Vy are all different. They all have different magnitude. Okay. But we will just focus on the motion on the y-axis, along the y-axis, because we are talking about the gas molecule hitting the shaded wall, So we just focus on the Vy. Now, and then we taking a look from this side, so to make it easier. So this is a shaded wall. We just look at the velocity along the y-axis. So this length is L. So what is the time between collision? What is the distance traveled between collisions along the y-axis? The distance traveled.
Distance traveled, velocity times time.
Yeah, but in terms of L, what is the distance traveled between the collision?
From that point.
2L. So.
Oh, between collision. Oh. Yeah, it's just a matter.
You hit the first time, this is the second time, is it? You hit the wall the first time and second time. So the distance between collision will be 2L. Okay. The distance between the collision will be 2L. And then the velocity along the y-axis is Vy. So the time between collision will be 2L over Vy. But turn out the proof is not included in us. You don't need to know about the proof. Okay? But still need to prove it to you. No, I don't have.
Anyone?
No. Spare mask.
Yeah.
Oh, then let's talk about the momentum. The change in momentum in each collision. So before hitting the wall, and after hitting the wall, it just be bound with the same velocity along the y-axis. So therefore, the change in momentum will be 2mvy. Now you write down the formula, we would just like mvy minus negative mvy. Now, actually, we have a pi 1 assumption here already. So that is all the collisions are elastic. We are apply the second assumption here. You see it? Let me go back to take a look. Is this like a second one? Yeah. Okay. Now this gas molecule hitting the wall for Fe2L over Vy. So let's go. Okay.
You're not taking into account how it's
Because we want to find a pressure. They're talking about the same mole. Yeah. So you have take a look at the force against time. So let's say this is the first time we hit the wall, and then after 2L over Vy, and then you hit the same wall again, is it? And then after another 2L over Vy, you hit the wall again, And then if you want to find the FH force on the wall, the FH force. So that means you want to find the FH force. So for the FH force, it will be the change in momentum over change in time. Is it? So then will be 2mVy divided by 2L over Vy. We have applied the third assumption here. We do ignore the time during the collision. We apply the third assumption here. We ignore the time during the collision. So you can find that the FH force on the wall by one molecule. This is one molecule only. It's mVy squared over L. Almost done, almost done.
Sorry, what's
Change in momentum.
Oh. Wait, so for the green line over there, from where to where it goes?
Just within the time to L over Vy. Just within the time to L over Vy.
Wait, so for the left side of the green line, does it touches the y-axis?
It doesn't matter at all. You just ignore the time during collision. No?
Also, basically just
Yeah. All right. Then this is just a force by one more gas molecule.
Oh yeah, never mind.
Now this is just the force by one gas molecule. So what you need to do is sum up the force of all the molecules. So you sum up all the force by all the molecules. That will give you the total force. The mass and L are constant. I just take it out. So this means you sum up all the Vy squared of all the molecules. Math, you do have learned about this. You?
Wait, so for integration and stuff.
Yeah. Also for differentiation. If there's some constant, you can take it out.
A number can be a constant.
Yeah. So we are taking the sum of this one. So you need to know that all the molecules are moving at different speed. So when you take this sum, first of all, we need to do, how can we do it? Now, there are big N numbers of molecules, and then times the FH of Vy squared. Do you use this symbol for FH in math? I do think you learn S1 ma. You use this symbol ma. How about for FH?
For sure.
FH. Hi. 係用呢個嗎？係啊。Mean that means FH, yeah. So the sum of something, that means the FA of that something times the total number, right? And so this one,
How do you find that?
what do you mean? How to find it? Now, just a second. Now, because due to random motion, we will say that the Vy square, average of Vy square, will be the same as a average of Vx square, and also the same as a Vc square, because the motion is random. They don't have a preferred direction of motion for gas molecule. Okay. So they're all moving in all directions. So that means for these three, they should be equal. Understand? Oh, 31 degrees Celsius outside. And then for the speed square, the average of the speed square, we need to use the Pythagoras theorem. Oh, sorry. I'll write it like this first. So C squared is Vx squared plus Vy squared plus Vc squared. Now, I'm not sure. Let me think about it, okay? So this is a cuboid. So it's with the side 1, 2, 3. So how do you find the diagonal?
You incorporate all the.
So you take the square root 1 square plus 2 square plus 3 square.
Sorry.
Is it?
Yeah.
Yeah. So similar.
We never got taught this.
So similar for the speed. So this is a cuboid. So you do have a relation that C squared is equal to Vx squared plus Vy squared plus Vc squared. Come on. Oh? Yeah, this is Pythagoras theorem. Do you want me to derive it? No need, then you should not have any confusion here. Hold on, let's move on. So, and then if I take the average of C squared, then it should be the average of Vx squared plus the average of Vy squared plus the average of Vc squared. Not difficult at all, is it?
Then since they're equal, just put them together, right?
Yeah, so we can make it like m times L times n times, this is C squared average divided by 3.
Oh, so smart.
All of them are equal. So each of them will be 1/3 of C squared average. Okay. C is the speed of the molecule. And then C squared average, it means you square it first and then take the average. I'll give you some example later on, but let's finish the formula first. N is the number of molecules. Small m is the mass of the molecule. How? Last, not yet. We haven't get the result yet, okay? Let's move on. Now, pressure can be written as a total force divided by the area. Now, the area is L squared. The area is L squared.
Actually, it's force over area, yes.
The area is L squared. Take a look at the diagram. It's L squared. So the force is half mn c squared FH divided by L, is it? And divided by L squared.
This is for cuboid, right?
Yeah. So L cube is the volume of the this is the volume of the container, is it? This is volume. So therefore we will get PV of 1/3 nm c squared FH. So this is our final formula. Area. The shaded area. 喂，你唔識揾 area 咩？ Do you know how to find this area?
Sir, can you go back a bit? Could you let us copy the formula? So that you can extend it to all of us.
咦？等陣。
Sir, undo.
I think there's something wrong here.
Undo.
Oh. I'll save it first. Let me see. This. Oh.
Sir, just hit undo.
Just a second, okay. I think I can just. Oh. I think there's some problem here. So let me okay start it again. 好，我就分嚟。